Hello and welcome back to the video series about ordinary differential equations. So you see, we are still in the beginning of the topic, and in today's part 2 we will first define the important notions we need. So for example, we will give the definition what we mean by an ordinary differential equation. However, before we do that, I first want to thank all the nice people who support the channel on Steady via PayPal or by other means. And please don't forget, in the description you find a link where you can download the PDF version and the quiz for this video. Okay, then without further ado, let's start with the important definitions we will need in this series. First of all, we will often deal with a set of functions called ck. And usually the domain of definition for these functions is given by an interval I. Hence, when you see capital I, it's always a subset of the real number line. Now in fact, most of the time in this series it will denote an interval, but sometimes it will denote a general open set. And in some other cases we might want that I stands for a union of two intervals. So you see, depending what we want to do later, we will stretch this definition a little bit, but here we will start with an interval I. And then the set ck is well defined as a set of functions. And here we immediately see the first special feature of this topic, because we will denote functions by a lowercase x. Hence, x is a function where the domain of definition is I. And it simply maps into the real number line. And now you should recall from real analysis that ck means that the function x is k times continuously differentiable. This means the kth order derivative of x exists and is a continuous function. Moreover, I should tell you here that the variable name we want to use for the function x is usually a lowercase t. This means we will write x of t. I tell you that because if we choose the variable name as t, we will use a dot for denoting derivatives. Hence, the first derivative here would be the function x dot. Then the second derivative would be x dot dot. And so on, and of course if we need too many dots, we will use the common upper index notation. Of course, in situations where the dot can be confusing, we will just use other notations. So for example, you know the common prime notation or the Leibniz notation. So please keep that in mind. Depending on the context or depending which book you read, you will see different notations for the derivative. However, the definition for an ordinary differential equation should be the same. Namely, it should be given by a combination of the derivatives of the function x. Indeed, we could write it down by a functional relation. For that, we take a continuous function capital F. And then we have different inputs, first of all the independent variable t. And then the function x and the derivatives of x up to some order. So as before, we could say the highest derivative is the kth order. Okay, and now this function with all the inputs should be equal to 0. Okay, so you see, in general, this is what we mean when we talk of an ordinary differential equation of order k. And maybe let's immediately look at an example for such an equation. So we could have t plus x plus 2 times x dot plus second derivative of x squared. And then this should be equal to 0. So there you see, this is a well-defined ordinary differential equation of second order. So the highest derivative that occurs in the equation gives us the order. And at this point, you might say it might be easier for us if we first start with first order differential equations. In fact, soon we will see why it is very helpful to start with the first order differential equations. Okay, but now it's helpful for the next definitions to abbreviate the term ordinary differential equation. From now on, we will simply write ODE if we need to keep it short and compact. Therefore, in the next definition, we will explain explicit ODEs of order 1. Here, explicit means that the derivative we are interested in is on the one side of the equation. And all the other terms, like the function x and the variable t, are on the other side. And both things we can rewrite with a function w. Hence, w gets two inputs, t and x. Moreover, we would say w is a function defined on two intervals. So we have the interval I for t and the interval j for x. And in this case here, both are simply intervals from the real number line. Okay, so in summary, you see here, this one is a special case of our general definition from above. However, it's the common one we will examine. That's because the two restrictions we have here are actually not big restrictions. Indeed, we will discuss soon why this case here is very general. But first I would say, let's look at an example of an explicit ODE of order 1. Hence, we already know on the left hand side we need to have x dot. And now on the right hand side, for example, we could have x plus t. So you see, the function w does not have to be very complicated. In fact, here the domain of definition is simply R2. Okay, but at this point you might remember what we have discussed in the last video. There we had examples where more than one variable is involved. Therefore, we might ask, is that also an example here for an explicit ODE of order 1? So we could write x1 dot, the first variable for x, is equal to the second variable x2 plus t. And then we could have a similar equation for x2 dot. Now this one could be x1 plus t. Now, important to note here is, these are not just two individual ODEs of order 1. Otherwise, it would not be allowed to mix the variables in this way. However, we can just put them together and call it a system of ODEs. And in fact, a system of ODEs looks exactly the same again. We simply have to write it as a vector equation. So the derivative of the vector x1, x2 is equal to a vector given by the right hand side here. And of course, this one can be expressed again by a function w. So w gets again two inputs, but now the second input is a vector instead of the variable x. And then you should see, if we call the vector x1, x2 simply x again, it has the same form as before. In other words, now we are able to define the term system of ODEs. More precisely, we would say we have an n-dimensional system of explicit ordinary differential equations of order 1. But you might already know, in the end, we will also just say ODE for such a system. Simply because from the form, from the looks, it's the same as our original definition. However, don't forget, the value x of t is now a vector. More precisely, we would say it's an n-dimensional vector. So in other words, our system now could have n equations here. Hence, the function w now also maps into Rn. Moreover, the domain of definition also changes for the second variable. Usually we would say we have u there, which is an open set in Rn. But as we said in the beginning, also that changes a little bit depending which problem we consider. Okay, but for the moment I would say we have a very nice definition what we mean when we say ODE. So this is a very general construct, but you see one important ingredient is still missing here. So now we know what an ODE is, but we remember for applications we are always interested in solutions of this ODE. So now the question is, what is a solution of a system of ordinary differential equations? Of course, it should be a function that is differentiable and can be put into the equation. And then it should fulfill the equation for all points t. However, there you already see, the domain of definition does not have to be the whole interval I. Indeed, it could be any subinterval which we can call t0 to t1. So this is an open interval, and now the solution function we could simply call alpha. So alpha is defined on this interval and it maps into Rn. More precisely, it has to map into the subset U. Simply because we want to put it into our function w in the second component, and then it should be well defined. Okay, there we have it. Solution means it fulfills this equation here. More concretely, the derivative of alpha at the point t is equal to w of t and alpha of t. So there you see, this is a well-defined equations of vectors, and it should be fulfilled for all t in the interval. So you see, now we can check this condition here pointwisely. And most importantly, you should see a solution is always a differentiable function. Okay, so we have a lot of definitions here, therefore let's close the video now with a concrete example. So this one should be very helpful to see what it means to be a solution for an ODE. And for this, let's look at a very simple system of ODEs. x1 dot should be equal to x2 and x2 dot should be equal to minus x1. So you see, this is a well-defined system for n is equal to 2. And moreover, we don't have a problem with the domain of definition, u is simply R2. And then the function wtx is equal to x2 minus x1. So you see, w does not explicitly depend on t. But please don't forget, t comes in again if you put in the solution alpha of t. Okay, so now if you look at a system, maybe you immediately see a solution. Indeed, I know sine and cosine functions fulfill something like that. In fact, alpha of t is equal to sine of t cosine of t does the job. Simply because we know the derivative of sine is the cosine and the derivative of the cosine is minus the sine function. Hence, we immediately have a solution of this system of ODEs. And now what one can do is to sketch the solution as its image. So we know the image of the solution lives in U, which is R2 in this case. And now we can sketch what happens to alpha of t when we start at t is equal to 0 and then increase t. In fact, you see what we get is a nice circle with radius 1. Moreover, now you can remember this image of the solution is called the orbit of the solution. Indeed, it's a dynamic picture that tells us what happens to the solution in the time variable t. Moreover, now you should also see that we easily find a second solution here. Namely, if we scale the vector by 1/2 and call the solution alpha tilde, then we see the ODE is also fulfilled. And there we get that the orbit is a circle with radius 1/2. Hence, our first result here is that a system of ODEs can have a lot of different solutions. Therefore, a question should also be which solution gives us the correct picture. Or more precisely, maybe we want a solution that goes through some particular points. And there we immediately have the questions, do we have a solution that goes through the points? And if we have it, is it unique? And exactly these questions we want to answer in this video course. Therefore, I hope that you are not scared off by all these definitions and come back to the next video. There we will make more geometric pictures such that you can understand the theory visually. So I hope we meet again and have a nice day. Bye.